Welcome to Big Data Analytics Technique and Tools. Module 4, the nuts and bolts of big data. Assembling a big data solution is sort of like putting together an erector set. There are various pieces and elements that must be put together in the proper fashion to make sure everything works adequately. And there are almost endless combinations of configurations that can be made with the components at hand. With big data, the components include platform pieces, servers, virtualization solutions, storage arrays, applications, sensors, and routing equipment. The right pieces must be picked and integrated in a fashion that offers the best performance, high efficiency, affordability, ease of management and use, and scalability. Big is a term relative to the size of the organization and more important to the scope of the IT infrastructure that's in place. The scale of big data directly affects the storage platform that must be put in place. And those deploying storage solutions have to understand that big data uses storage resources differently than the typical enterprise application does. These factors can make provisioning storage a complex endeavor, especially when one considers that big data also includes analysis. This is driven by the expectation that there will be value in all of the information a business is accumulating and a way to draw that value out. As data sets continue to grow with both structured and unstructured data, and data analysis becomes more diverse, traditional enterprise storage system designs are becoming less able to meet the needs of big data. This situation has driven storage vendors to design new storage platforms that incorporate block and file-based systems to meet the needs of big data and associated analytics. Big data key storage ideologies. We have the capacity, security, latency, access, flexibility, persistence, cost, application awareness, and small and medium business. Meeting the challenges posed by big data means focusing on some key storage ideologies and understanding how those storage design elements interact with big data demands. Capacity. Big data can mean petabytes of data. Big data storage systems must therefore be able to quickly and easily change scale to meet the growth of data collections. These storage systems will need to add capacity in modules or arrays that are transparent to users without taking systems down. Most big data environments are turning to scale-out storage technologies to meet that criterion. Big data also means many large and small files. Managing the accumulation of metadata for file systems with multiple large and small files can reduce scalability and impact performance, a situation that can be a problem for traditional network-attached storage systems. Object-based storage architectures, in contrast, can allow big data storage systems to expand file counts into the billions without suffering the overhead problems that traditional file systems encounter. Object-based storage systems can also scale geographically, enabling large infrastructures to be spread across multiple locations. Security. This data may not be different from what current IT managers must accommodate. Big data analytics may need to cross-reference data that have not been commingled in the past. And this can create some new security considerations. In turn, IT managers should consider the security footing of the data stored in an array used for big data analytics and the people who will access the data. Latency. Storage systems must be able to grow rapidly and still maintain performance. Latency produces stale data. That is another case in which scale-out architectures solve problems. The technology enables the cluster of storage nodes to increase in processing power and connectivity as they grow in capacity. Object-based storage systems can parallel data streams, further improving output. Most big data environments need to provide high input-output operations per second or IOPS performance, especially those used in high-performance computing environments. Virtualization of server resources, which is a common methodology used to expand compute resources without the purchase of new hardware, drives high IOPS requirements, just as it does in traditional IT environments. Those high IOPS performance requirements can be met with solid-state storage devices which can be implemented in many different formats, including simple server-based cache to all flash-based scalable storage systems. Access. The quest to create business value drives businesses to look at more ways to cross-reference different data objects from various platforms. Storage infrastructures that include global file systems can address this issue, since they allow multiple users on multiple hosts to access files from many different back-end storage systems in multiple locations. Flexibility. Big data storage infrastructures also need to account for data migration challenges. At least during the startup phase, ideally, data migration will become something that is no longer needed in the world of big data, simply because the data are distributed in multiple locations. Persistence. Big data users are often saving data longer because they are part of a historical record or are used for time-based analysis. The requirement for longevity means that storage manufacturers need to include ongoing integrity checks and other long-term reliability features, as well as address the need for data in-place upgrades. Examples are medical information, which is often saved for the life of the patient, and financial information, which is typically saved for 7 years. Cost. Storage deduplication has already entered the primary storage market, and depending on the data types involved, could bring some value for big data storage systems. The ability to reduce capacity consumption even by a few percentage points provides a significant return on investment as datasets grow. Other big data storage technologies that can improve efficiencies are thin provisioning, snapshots, and cloning. Thin provisioning operates by allocating disk storage space in a flexible manner among multiple users based on the minimum space required by each user at any given time. Snapshots streamline access to stored data and can speed up the process of data recovery. There are two main types of storage snapshot: copy on write or low capacity, and split mirror snapshot. Utilities are available that can automatically generate either type. Disk cloning is copying the contents of a computer's hard drive. The contents are typically saved as a disk image file and transferred to a storage medium, which could be another computer's hard drive or removable media, such as DVD or a USB drive. Application awareness. Initially, big data implementations were designed around the application-specific infrastructures such as custom systems developed for government projects or the white box systems engineered by large internet service companies. Small and medium business. The value of big data and the associated analytics is trickling down to smaller organizations, which creates another challenge for those building big data storage infrastructures. Creating smaller initial implementations that can scale yet fit into the budget of smaller organizations. Building a platform. Big data application platforms are unique. They need to be able to handle massive amounts of data across multiple data stores and initiate concurrent processing to save time. This means that a big data platform should include built-in support for technologies such as MapReduce, integration with external, not only SQL or NoSQL databases, parallel processing capabilities, and distributed data services. It should also make use of the new integration targets, at least from a development perspective. Characteristics and features of big data platform. So we have support for batch and real-time analytics, alternative approaches, available big data mapping tools, big data abstraction tools, business logic, moving away from SQL, in-memory processing, built-in support for event-driven data distribution, support for public, private, and hybrid clouds, and consistent management. Support for batch and real-time analytics. Most of the existing platforms for processing data were designed for handling transactional web applications and have little support for business analytics applications. That situation has driven Hadoop to become the de facto standard for handling batch processing. However, real-time analytics is altogether different, requiring something more than Hadoop can offer. An event processing framework needs to be in place as well. Fortunately, several technologies and processing alternatives exist on the market that can bring real-time analytics into big data platforms. And many major vendors such as Oracle, HP, and IBM are offering the hardware and software to bring real-time processing to the forefront. However, for the smaller business, that may not be a viable option because of the cost. For now, real-time processing remains a function that is provided as a service via the cloud for smaller businesses. Alternative approaches. Transforming big data application development into something more mainstream may be the best way to leverage what is offered by big data. This means creating a built-in stack that integrates with big data databases from the NoSQL world and creating MapReduce frameworks such as Hadoop and distributed processing. Development should account for the existing transaction processing and event processing semantics that come with the handling of the real-time analytics that fit into the big data world. Creating big data application is very different from writing a typical CRUD application for a centralized relational database. The primary difference is with the design of the data domain model, as well as the API and query semantics that will be used to access and process that data. Mapping is an effective approach in big data. Hence, the success of MapReduce, in which there is an impedance mismatch between different data models and sources. An appropriate example is the use of object and relational mapping tools like Hibernate for building a bridge between the impedance mismatches. Available big data mapping tools. Batch processing projects are being serviced with frameworks such as Hive, which provide an SQL-like facade for handling complex batch processing with Hadoop. However, other tools are starting to show promise. An example is JPA, which provides a more standardized JEE abstraction that fits into real-time big data applications. The Google App Engine uses data nucleus along with Bigtable to achieve the same goal. With Gigaspace's use, OpenJPA's JPA abstraction combined with an in-memory data grid. Red Hat takes a different approach and leverages Hibernate object grid mapping to map big data. Big data abstraction tools. There are several choices available to abstract data, ranging from open source tools to commercial distributions of specialized products. One to pay attention to is Spring Data from Spring Source, which is a high-level abstraction tool that offers the ability to map different data stores of all kinds into one common abstraction through annotation and a plug-in approach. Of course, one of the primary capabilities offered by abstraction tools is the ability to normalize and interpret the data into a uniform structure, which can be further worked with. The key here is to make sure that whatever abstraction technology is employed deals with current and future data sets efficiently. Business logic. A critical component of the big data analytics process is logic, especially business logic, which is responsible for processing the data. Currently, MapReduce reigns supreme in the realm of big data business logic. MapReduce was designed to handle the processing of massive amounts of data through moving the processing logic to the data and distributing the logic in parallel to all nodes. Another factor that adds to the appeal of MapReduce is that developing parallel processing code is very complex. When designing a custom big data application platform, it is critical to make MapReduce and parallel execution simple. That can be accomplished by mapping the semantics into existing programming models. An example is to extend an existing model such as session bin to support the needed semantics. This makes parallel processing look like a standard invocation of single job execution. Moving away from SQL. SQL is a great query language. However, it is limited, at least in the realm of big data. The problem lies in the fact that SQL relies on a schema to work properly, and big data, especially when it is unstructured, and does not work well with schema-based queries. It is the dynamic data structure of big data that confounds the SQL schema-based processes. Here, big data platforms must be able to support schema-less semantics, which in turn means that the data mapping layer would need to be extended to support document semantics. Examples are MongoDB, Couchbase, Cassandra, and the Gigaspace's document API. The key here is to make sure that big data application platforms support more relaxed versions of those semantics, with a focus on providing flexibility in consistency, scalability, and performance. In-memory processing. If the goal is to deliver the best performance and reduce latency, then one must consider using RAM-based devices and perform processing in memory. However, for that to work effectively, big data platforms need to provide a seamless integration between RAM and disk-based devices in which data that are written in RAM would be synced into the disk asynchronously. Also, the platforms need to provide common abstractions that allow users the same data access API for both devices and thus make it easier to choose the right tool for the job without changing the application code. Built-in support for event-driven data distribution. Big data applications and platforms must also be able to work with event-driven processes. With big data, This means there must be data awareness incorporated, which make it easy to route messages based on data affinity and the content of the message. There also have to be controls that allow the creation of fine-grained semantics for triggering events based on data operations such as add, delete, and update and the content, as with complex event processing. Support for public, private, and hybrid clouds. Big data applications consume large amounts of computer and storage resources. This has led to the use of the cloud and its elastic capabilities for running big data applications, which in turn can offer a more economical approach for processing big data jobs. To take advantage of those economics, big data application platforms must include built-in support for public, private, and hybrid clouds that will include seamless transitions between the various cloud platforms through the integration with the available frameworks. Examples abound such JClouds and cloud bursting, which provides a hybrid model for using cloud resources as spare capacity to handle the load. Consistent management. Building a big data platform is no easy chore, especially when one considers that there may be a multitude of right ways and wrong ways to do it. This is further complicated by the plethora of tools, technologies, and methodologies available. However, there is a bright side that stresses flexibility, and since big data is constantly evolving, flexibility will rule in building a custom platform or choosing one off the shelf. Bringing structure to unstructured data. Unstructured data has little value in its native format. Big data analytics are needed to extract the value from this data. The importance of integrating structured and loosely unstructured data cannot be overstated. There are a few enabling technical strategies that make it possible to sort the wheat from the chaff. Some tools combine this capability with in-place transformation at the target database, as well as with change data capture to synchronize, source, and target again without the overhead of a middle tier. The overarching principle is real-time data integration, in which reflecting data change instantly in a data warehouse can create downstream analytics. Semantic Resources Description Framework, or RDF, triple the store and creates an alternative to traditional relational databases. It is not relational in the traditional sense, but it maintains relationships between data elements, including external ones. One of the most powerful aspects of semantic technology comes from the world of natural language processing. This is a powerful mechanism to extract information from unstructured data and combine it with transactional data, enabling deep analytics. The trend for this tool is to move toward recognition of further useful entities, such as product names, brands, events, and skills. Processing power. There is a simple relationship between data analytics and processing power. The larger the data set and the faster that results are needed, the more processing power it takes. However, processing big data analytics is not a simple matter of throwing the latest and fastest processor at the problem. It is more about the ideology behind grid computing technologies. Big data involves more than just distributed processing technologies like Hadoop. It is also about faster processors, wider bandwidth communications, and larger and cheaper storage to achieve the goal of making the data consumable.